And that's a more detailed layout of our agenda for the day. Yeah, and then please, this is not a talk show. It's not just you sitting there and listening to me. Feel free to make your contributions at any point. Don't wait until we get to the end. At any point, just unmute and then you make your contribution. Or if there's something that's unclear, you give me a signal and then we'll try to unpack things. Is that okay, Fortunate?
Hello. Yes, that's okay.
All right, cool. I also see that we have people joining. Okay. Before we get started, can I just get maybe one or two people to just highlight what your specialization is? Just any two people. Sindiswa? Okay, just any two people to share with me what you are specializing in study-wise.
We're doing the postgraduate diploma in data analytics, if that's what you're asking, sir.
Give that to me a bit slower. PG dip in.
Data analytics.
All right.
Yes, sir.
All right. And then I presume that that's everybody. That's the whole class. We are not a mixed class.
Correct.
All right. Cool. Thank you for the feedback. So I looked at your schedule and I did see that you've already done something on supervised learning. Okay. So I'm not trying to take you back or ask you anything tricky, but I may ask you just some prompting question to get a sense of where exactly you are. Okay. So when we say unsupervised, all we essentially meaning is that we are using some kind of machine learning, and then we are working with unlabeled data. So we are not making use of labels in the data. That's all that it means. Okay, now if we don't have labels, it means that our focus is a lot more on I'm just trying to get my highlighter. It means that we are in a way focusing more on discovering of patterns in the data. That would be the focus. Okay. In contrast, when we are doing supervised learning, what we're doing is maybe trying to learn to predict something. Okay. Okay. I'm going to try and illustrate further using this example. I'll just give you a moment to just look at that illustration here. All right. So let me just try to illustrate. And I'm trying to illustrate what we mean by supervised learning. All right, so there's this famous data set. You can look it up on the internet. It's called the IRIS data set. Okay, now what is this IRIS data set? It's about some scientists that some years back, they looked at these flowers that you are seeing here on the screen here. So there's something called Setosa. It's the name of the flower. There's Vescala, and then there's also Virginica, which is another plant. So what they did was they took measurements, one, two, three, four measurements. So a flower has what's called a petal and then a sepal. And then what they did was that they measured the length and then the width of the sepal as well as the petals of each of these flowers. Okay, so they did the measurements, and then of course they documented what flower it was in this fifth column here that I've tried to highlight there. Okay, how did they know it's a Setosa? Well, they are experts in this field, so they could tell they were able to identify the plant. Okay, and then we have all these measurements here. Now, of course, this is an illustration. In reality, there's hundreds and hundreds of these measurements. Okay. Can somebody tell me what we can use this data for? Remember, I said that the experts were able to identify the names of these flowers by looking at it. And then they were able to, they also took the measurements. They took the, what did they take? The length of the sepal, the length, and then the width of the sepal. And then they also took the length of the petals as well as the width of the sepals. Okay. Now I'm asking, assume we have that data. What can we use it for? Can somebody hint at what the use of such data could be? Okay, let me check in the chat.
Yeah, I think basically it's just to determine the category of a plant, or rather of that leaf, whether it's Setosa or Virginica. So based on the size of the sepal width or length, then determine which category does fall within those three types that we have mentioned there.
Okay. Ketley says to categorize the data. I get that. I see there's another hand from Jesse. Jesse, go for it.
Okay, maybe it can also be used to train an algorithm that can then later on identify these kind of flowers and maybe classify them.
Based on
the sepal width, petal length, and petal width.
Exactly. So what Jess is telling us is that this data can be used to train a model. What do we mean by training? We already have this mapping of the different measurements here mapped to the type of flower that it is. Okay. So later on, remember we said that this was done by experts. So later on, what we can do is, I'm trying to get my pointer here. What we can do is a non-expert like myself we can take measurements. So we might be able to maybe get the measurements. I don't know, I'm just making this up. Maybe there's something called 4.3, right? Maybe 2.7, okay? And then the petal length there maybe is 1.2. I'm just fabricating this up. Maybe 0.1, right? But I don't know what type of flower it is. Now, what Jesse is saying is that we can have a model where it takes these lengths and widths and then is able to tell us and say, based on this and based on the training that's been done, this must be a maybe Virginica, for example, or maybe it's a Setosa. That's what you meant to say, Jesse, right?
Yes, that's it.
All right. So this is a perfect example of what we refer to as supervised learning. It's supervised because there's data to learn from. Okay. Now, in contrast, when we say unsupervised learning, it means that we don't have this label. We don't know whether it's a Setosa, if it's a Virginica. We don't have that. Okay. That's the meaning of unsupervised learning. All right. Now, like we said, when we are doing unsupervised learning, it means that we are now interested in what? In the patterns that the data has. We want to discover what are the patterns in the data. And so it boils down to a number of what we can call learning tasks. So one of them is clustering. There's dimension reduction. There's also association rule mining. Okay, so we can maybe add here and say association rule. We can either say mining, or we can maybe say association rule discovery. We can use the word discovery. That's what we are trying to say here, discovery. Okay, now I've deliberately blared association rule mining because I doubt we'll have the time to go over this, but I've highlighted it there nonetheless, so you can maybe exploit in your own free time. Our focus for today is on clustering. This is where we'll focus on. And then next week, we'll shift attention to data dimension reduction. Okay, so this is where the bus is going. Is that clear, Fortunate?
Yes, it's clear. Thank you.
All right. Now, when we say clustering, what does it mean? You have already given me the answer from what Ketley says. He says to group the data into something. So when we say clustering, it means that we want to group data using some kind of a measure of association. Okay, then we create some kind of grouping. That is all that clustering is. Okay. Now I'm going to maybe ask you as a class here. Let's assume that you as a class here, you are data points. Okay. What are some of the ways in which we can group ourselves as a class? One, to Miss Singh.
Location.
Just elaborate for me.
Location, where we stay.
Okay, so what Tab is saying is that we could use our location. Okay, maybe we say, okay, we say this is a list of people maybe that live in KwaZulu Natal, and there may be another list of people that live in the Northern Cape, maybe another. You get where I'm going. So we are using a location. Okay. Somebody says experience with technical tools. Again, maybe we can maybe say that this is those with we might say people with Python experience, like he said there. Okay. So we might create a group of people that have Python experience. Lerato says gender. Yes, we can maybe just have two groups, male and female. Okay, let's not get too complex there. We can have two groups. Andrine.
I was going to say the order in which we registered, because the institution already basically groups us by the first batch who registered as group 1, the second batch as group 2, and 3 and 4, for example.
Yeah, so we could maybe say if you registered between January and Feb, you are group 1. Feb to April, group 2, and so forth. Thank you for that. What else? By birth of month, yes, we can maybe have 12 groups. Those that were born in January, those born in April, and so forth. We could do that. Okay, you get the idea. So there's different ways that we can group ourselves. So there's essentially, I want you to pick out two things from the examples that you've given me. One, it's that there's different ways that we can do the grouping. And that's exactly what makes clustering interesting. It makes it interesting. It also makes it, I would say, a little bit challenging. A little bit challenging because you've given me several ways that we can cluster. So when we say we want to do the grouping, you can already see that there's different ways to do the grouping. Now, which criteria are you going to use? Okay, so that in a way complicates the task of creating groups. Okay, we are using these examples to simplify the conversation, but in reality, what you've just highlighted here makes the task of clustering very complex. The idea is what you've already shared. If we look at a cluster, for example, this is A. Let's say A. And then we maybe have B, right? Cluster B. Okay. The samples that are in cluster B, they have to be the same in some way, or they should be similar, right? Similarly, the data samples that are in cluster A, they have to all be similar. Okay. What can you tell me about the samples in group A versus group B in terms of similarity? How should they be? They should be different, very different, right? All right. Now, there's several ways that we can do the clustering. So one way is to create partitions, such as the ones that you've just told me. So this is an example of maybe we can call it partitional clustering. Why? Because we have the data, and then we group it into different partitions. Partition this, partition that. Okay, now another way to do the clustering is to do the clustering as a hierarchy. Okay, so what do I mean by hierarchy? Let me see if I can think up an example. So we could maybe start by saying, let me use one criteria, which was location, right? Let me use that as an example. So we can maybe just have we can have maybe one cluster that we call maybe Gauteng, right? So this is one cluster. And then maybe Western Cape. Okay. This is another cluster. Okay. Now, you would agree with me that Gauteng is a big place, right? Anybody who agrees with me on that? I'm getting a yes. Okay. We can also have perhaps maybe different parts of Gauteng. Okay, now, those of you that are familiar with Gauteng, you can help me fill in the blanks here. Can somebody give me one name? Maybe give me a town in Gauteng. Just one. Just unmute and give it to me.
Pretoria.
All right, Pretoria. What else? Joburg, right? What else? All right. Now, you would also agree with me. Okay, let's say that this is Pretoria. You'd agree with me that Pretoria itself, it might be made up of several suburbs. Am I correct? Yes, no, yes?
Yes.
Maybe different suburbs. Okay. You get the idea. The same thing can be said about the Western Cape. We have different cities in the Western Cape. The cities themselves can be broken up in different suburbs and so forth, right? That story continues. And then maybe collectively, we are maybe all into one cluster that we can maybe call, let's just maybe say South Africa. It's a cluster, right? Why do I say it's a cluster? It's a cluster because South Africa exists maybe in a continent. You get the idea. So you can see here that in this illustration here, we don't have partitions. What we have is a hierarchy. Are you with me? Ketley says, in the above example, can it be hierarchical if people are clustered into beginner, intermediate, professional? It can be like that. It will have to be, how are you clustering? What I want you to pick out when we say hierarchical clustering, it's a fact that it's classed as a hierarchy. It's one above the other. Okay, so in terms of what this really means, Ketley, what this means is that in terms of the meaning of this is that whatever is below here, it in a way is a member of the clusters upwards. As an example, every clusters that we put below here, these are falling in the Gauteng area. So if you organize it that way, we can call it a cluster. There has to be a hierarchy from top going downwards. Are we together? Is that clear, Ketley? And then speaking of, there's somebody that gave an example of, let's say we can cluster based on the days of registration, which I agree. Okay, we can have a cluster. What's a cluster? Maybe we can group ourselves by the departments that we are in. And then where are these departments? These departments tend to be under a certain faculty. Okay, that's another level of hierarchy. Where is this faculty? At a specific institution. So you can see that we can have that as we can cluster ourselves using a hierarchy. Yes, there has to be some level of hierarchy, one above the other. Are we together? Sesetu, is that clear?
Yes.
All right. Now, if that's clear, I thought of just letting you know, in terms of our focus, we are going to focus more on partitional clustering. Nonetheless, I thought it's wise that we just give you an overview of hierarchical clustering, just so you are aware of the different approaches of clustering. Why are we looking at partitional clustering? It's because we just won't have the time to look at everything, but you need to be aware of the bigger picture. Okay. All right. Now, when we say clustering, it's actually one example of what? unsupervised learning. Okay, is that the only example? There is others, but clustering is one example. Okay, and once you have the clusters, you can do something called cluster analysis. Okay, and then we do have methods that we can use to do the cluster analysis. The thing about clustering is that we need some kind of what? Some kind of criteria that we are using to do the classification. And we refer to these more formally as decision boundaries. Okay. So why should we put this in cluster 1 and cluster, or not cluster 2? Okay. It's because of some criteria that we are using. Okay. And then the key word is that this will usually be done with using what? Some kind of unlabeled data. Okay. Any questions on clustering, what it is? All clear? Suzanne? Suzanne? Or is it Susan? You have to correct me. Okay, I'll take
Yes,
that
it's
as a...
Susan.
All right, I'll take that as a yes, it's clear. Any questions from your side, Susan?
No, sir.
So far, so good, right?
Yes.
Musokuhle. Misokuhle.
Yeah. Okay, so I see we've got many types of unsupervised learning. So let's say you just get some data. Is there some guidelines in which are there to guide you to say, okay, in this data, you can try and approach it with clustering, or it's just try and error, or maybe we are still going to get there?
Let me push pause on that question. What we can do, Ms. Okuhle, is that we can I won't answer it now, but maybe when we get near the end, we can come back to your question. You're welcome to ask it as it is, or maybe you ask it differently based on what we are going to chat about. Is that okay?
It's okay. It's okay.
All right. All right. So just as an example, I have some data here. This data is on, let's say, from a retail outlet. Okay, so you can see that in this column, what we have the number of items that were bought, and then in the third column, there's a price. Now, assume that the price here is the unit price. So it's not the total, but the unit price of each item. And then I've made your work easy. Here we have clusters 1, 2, and then 3. All right. What can you tell me about these clusters? How can you describe these clusters? Sesetu.
I think the clustering was either by the number of items or the price, because with the number of items in cluster 1, they are fairly closer, as you recently mentioned, the previous slide mentioned, as well as cluster 2's number of items is they're closer to each other than the other clusters.
So Sesetu says, Sesetu is seeing it in terms of number of clusters, number of items. Okay. Okay. All right, I'll take that. Anybody else with a different view? Ms. Sokuhle.
Yeah, I think this was done in 2 dimensions where you have to consider the number of items and the price. So if you look at cluster 1 and cluster 3, the number of items are almost similar, but the price is very, very different. So I think, yeah, they use the number of items and the price. Thanks.
All right. Now, whilst you are on it, what can you tell us about cluster 1, cluster 2, cluster 3?
So cluster 1, you have items, few items, so we can say less than 5 items, with the price range or in thousands. And then cluster 2 is similar to cluster 1 in terms of price range that is in the thousands, but you've got more items there, hence it's in its own cluster. Then cluster 3, you've got few items, but the price is very, very low.
All right. Thank you, Ms. Okuhle. So remember that these clusters are in a way groupings of, let's call them customers, right? Remember we said this is coming from a retail outlet. So this is a grouping of customers. And then like Ms. Okuhle has said, cluster 1, we can say that these are customers that buy a few expensive things. Right, Ms. Okuhle?
Yes, sir. Yes.
If we look at cluster 2, we can maybe say that this is a group of customers that buy a larger number of expensive items. So it's a large number of items and then they are not cheap. Okay, cluster 3, it's another group of customers. Who are these? A few number of items, cheap items. So these are the 3 groups that we have. And then Andrine there has summarized it up for us. Cluster 3, lower number of items, but let's not say but, we can say low number of items and low prices. 2, yes, higher number of items that are pricey. You are correct on that. So this is an example of clustering. Okay. Now you need to understand that the example on the screen is deliberately simple. That way we are able to inspect and then we can make the decision. Okay, we were able to draw those red lines and come up with cluster 2, 1, and 3. Okay, that's deliberate. In reality, it won't always be as simple as that. Okay, but the takeaway from here, it's this idea of clustering based on some kind of criteria. Okay. Now, I did give you a hint when we started that clustering is what? It's a difficult problem. Okay, what makes it difficult? I would like you to look at this figure below here. Let's look at figure A. Let's look at figure A. Figure A is here. Okay, here. All right, figure A is here. Now, in B, figure B, we are doing some clustering, and you can see we've come up with this cluster here. There's that one there, as you can see, and then that one there. This is one way. How many clusters do we have in B? Jesse. In B, how many clusters do we have?
3.
All right. Now come to C. The data points haven't changed. We've done the clustering, but how many clusters do we have? Jesse. We now have 4. Thanks, Bianca. We now have 4. Now, the point here is there's no wrong or right clustering. B and C, they're just different ways of doing something. Okay? And the point here is just to emphasize that there's different ways in which you can do the clustering, and that's what makes it what? It makes it a very difficult problem. Okay? So what we need is we do need to have some objective way of assessing our clustering, and we will get there in a moment. Okay, but before we go there, we've already had this conversation on the types of clusters. By now, you know that we can do partitional clustering, and then we can also do hierarchical clustering. We've already gone over that. Which one should you use? It depends. And again, just to emphasize that time may only allow us to look at partitional clustering. But you're welcome to venture into hierarchical clustering. Okay. If I could maybe just preempt where we are going, we do have algorithms that are used for partitional clustering. Okay. And then we also have algorithms that are specifically meant for hierarchical clustering. Okay, you're welcome to investigate that. Okay. Now, one of those algorithms is what's known as the k-means algorithm. Okay, so it's an algorithm that is used to do partitional clustering. Okay, how does this work? So k means that it will try to create k partitions, or the other word for partition is that k clusters. What is k? K is a number, 2, 3, 4, and so forth. You will have to decide on how many clusters you want. Okay? And how is the clustering done? It starts off with, let's say, a random initial partition. So the data is randomly grouped. And then what the algorithm will do is that it goes through several iterations, and then on each iteration, there's a reassignment of the samples to the clusters. We'll look at an example. Okay. When does the iteration come to an end? It comes to an end when there's no more reassignment that is happening. Then the algorithm comes to a halt. Okay, we'll get to an example in a moment. So how is this done? If I could just preempt where we are going, we said that it starts off with a random number of partitions. Okay, so to give you an idea, let's say we have 3 partitions, partition 1 to 3. So the algorithm will look for what we call the total square error. And what's the idea when you are doing the grouping? It's to minimize the total square error. Okay. Here's a summary of the k-means algorithm. Like I said, it starts with some initial partition with k clusters. What is k? K is the number of clusters. It could be 3, 4, maybe 5, maybe 10. We don't know. And then what happens is that it will try to generate new partitions by assigning each sample to the closest cluster center. Okay, again, just bear with me. I will get to an example. And then once that's done, you have to compute the new center of each of those clusters that emerge. Okay, and then thereafter, this whole process gets repeated. So 3, 2, 1 steps get repeated. When does the algorithm halt? When there's no more reassignment that is happening. Okay, let's see if we can look at an example. Hope everybody can see slide number 14. Okay, so here we have samples 1, 2, 3, 4, 5, right? And then these samples have features what? A and B. Sesetu, are you following?
Yes.
All right. Now remember the A and B, we can easily say X and Y, okay, which you are familiar with. So we've labeled sample 1, 2, 3, and 5, these samples that you are seeing here. We've labeled them as coordinates. So there's x1, what's x1? 0, 2, right? Where is the 0, 2 coming from? It's coming from here. Sesetu, are you with me?
Yes.
Okay. What is x2? Sesetu, x2 is Jesse, what is our x2?
0, 0.
X2 is 0, 0. Where is the 0, 0 coming from? It's coming from there's 0, there's another 0. Can you see my marker? All right.
Yes.
And then x5, fast forward to x5. x5 is pertaining to sample number 5. What is a coordinate? Coordinates are 5, 2.
5, 2.
All right. So let's go through we're going to go through this k-means algorithm. All right. So what's step 1? Step 1 is two things. Firstly, we do the initial partitioning, and then we do what? We compute the centroids. But centroids is just a fancy way of saying we find the center of that cluster. So in this example, how many clusters do we have? We've decided that we just have what? 2 initial clusters. We are calling them C1. I hope you can see here, C1. Then the other one is what? C2. These are our 2 clusters. Okay. Mr. Kuchle, what do we have in C1 or cluster 1? What do we have? We have samples. Mr. Kuchle.
Yes, we've got sample 1, sample 2, and sample 4.
Exactly. And then in cluster 2, what do we have? Sample 3 and then sample 5. So the next thing that we need to do is to find the centroid. In other words, what is the center of these clusters that we've created? Okay, the formula for this is what you are seeing on the screen here. Now, instead of me reading this formula for you, which you can read, I'm going to try and show you how this formula applies. Okay, but before we go there, if I can ask you, in this case, what is the value of our k? Lerato says 2. It's 2 because we have how many clusters? We have 2. So our k is 2. All right, you are correct, Lerato. How did we come up with 2? Lerato. Okay. For now, we just decided that we want 2 clusters. Okay, so we just came up with 2. It was just randomly arrived at. Okay, there's no science that went into how that 2 came about. All right. Is everything clear so far? This is step 1 of the algorithm. And then just to be clear, this initial assignment that we have here, we said it's just done randomly. So why is sample 1 to 4 assigned to cluster 1? No, this is just random. It's an initial starting point. Is that clear? All right. Now we need to figure out how to calculate the centroids of the clusters. Okay. Now, firstly, you can see here in my slide that we have M1 here. M means it's just the notation we are using to denote the centroid. So M1 means the centroid of cluster 1. M2 means the centroid of what? Cluster 2. Okay. Firstly, you see these 3, which is the denominator. As I said, do you see these 3 here?
Yes.
The 3 is there because we have how many samples in cluster 1? How many samples do we have in cluster 1? We have
3.
We have 3. So that's where the 3 is coming from. Okay. So what we then do for the numerator is, and what are these samples? It's 1, 2, and then 4. Let me see if I can highlight them on the board. My mouse is misbehaving. Okay, so it's 1, 2, and then 4. Okay, so we start by looking at the value of x. Remember, we said we can view it as x comma y, right? So what is the value of x in x1? What is the value? It's a set. Excuse me. What is the value?
0.
It's a 0. So this is where this 0 here is coming from. You with me, right? And then in x2, what is the value of x?
0.
It's 0.
0.
So that's where the other 0 is coming from. Then we go to sample number 4. What is the value of x?
5.
It's
5.
5. Hence we have this 5 here. Okay. The moment we do that, we then do the same thing for our y. Okay, what is the value of y here in x1?
2.
It's 2. Okay. And then you have your 0 and then your 0. So you see where understand where all these values came from? So if you simplify this, it will work out to 1.66, 0.66. In other words, we are saying that this is the centroid of cluster 1. And then you repeat the process for cluster 2. This is what would be the centroid, 3.25, 1.00. Okay. This is still just step 1. All right. Are we all clear on step 1? Any questions? Going once, going twice? All right. So let's see what we do in step 2. In step 2, here's what we are. Let me try to see if I can illustrate for you what we are trying to do here. What we've done is that we roughly have these. Let me not say that okay. We've in a way computed Okay, I'm looking for the eraser. Okay, in step 2, what we are trying to do is we've computed oops, I'm using white to write. It won't work. White on white won't work. So we have computed M1. Okay. We've also computed M2. Okay, M2. So one point. Okay. So you have to imagine that we have something like this. Okay, so this is our y coordinate, this is our x coordinate. Okay, now I'm just illustrating these are not actual values, but we have something like again, I'm not being actual, but maybe our M1 is somewhere there, right? And then our M2 is there. Okay, and then we have other points. So what we're trying to do is we want to check, we look at each of the different data points here. Okay, maybe there's one, that, maybe that. These are just illustrations here. We have 5, right? We have 5. So what we are trying to do is that we are checking to see which center is a sample closest to. So we are in a way checking to say, we in a way check to see what is the distance of this sample from here to that center, and then from here to that center. Okay, then we make a comparison. That's what we're doing in step 2, because for a sample to be in a cluster, it means that it has to in a way be closer to that centroid of that cluster. Do you agree with me in terms of what we are trying to do? All right. So that's visually, that's what you should keep in mind. And then the formula for that is we can maybe look at what we call the Euclidean distance. Don't let this jargon mislead you. What we mean by Euclidean distance, think of it like this. You have, this is what we call the Euclidean space. Just think of our x coordinate there. Okay. We have it something like this, right? And then maybe you have a point here, maybe another point there. So we just want to check what is the distance here across this Cartesian plane. What's the Cartesian plane? The XY plane. That's what we are calling the Euclidean distance. Okay. Are you with me, as I said, on that?
Yeah.
Okay. So said to imagine with me that can you see my illustrative 1 and 2, which I've placed on the screen there on the XY axis? Can you see?
Mm-hmm.
Now imagine that I have maybe A and then B. What can you say is the distance there?
Wouldn't it be 1?
Okay, I agree with you. Again, I'm just using that for illustration. We can maybe say 1. So this whole fancy formula, it's in a way just being used to gauge the distance of a sample from a given centroid. And then the reason we're looking at the Euclidean distance is because there's different measures that you can consider. We won't dive into that, but Euclidean is very simple, and so we are going to use it. Okay? So think of the Euclidean distance as our criteria. Okay. How is it done? How do we measure the distance? So over here, what I have here, it's just a a repeat of the centroids that we've already calculated, so we can be looking at it. Okay. Now, bottom left is our formula. And again, instead of reading out the formula to you, which you can do, I'm going to try and show you the formula in action. Firstly, when we say m1, x1, it's just a way of saying we want to look at the distance of x1 from m1. What is m1? So said m1 is
The
centroid of cluster 1. And how is this done? All right. So let's look at x1. x1 is what? 0,2, right? So what you need to look at is this, the centroid here, it's 1.6, 0.66. Now again, I want you to think of it in terms of x, y. So let's look at the x part. Okay, so we simply find out that the difference between the x in the centroid versus the x in the sample. So in a way, it's like saying 1.66 minus 0, what we get? We get 1.66, right? And then the formula says we square it. Then we say plus. What is 2 minus 0.66? Can somebody tell me? 2 minus 0.66. Somebody work it out and give it to me. Two minus 0.66. What's the answer?
1,34.
1,34, which is what we have on the screen there. Okay. The question is, where did the 2 come from? The 2 is a y part of our x1. Where did the 0.66 come from? The 0.66 is a y part of our centroid. Okay. It's coming from the centroid there. Bianca, is that clear?
Yep, understand.
All right. And then the formula says that we have to square each of these. Can somebody tell me why we square them? Anybody wants to tell me why we square?
Well, the distance can't be negative. So even though it's negative inside the brackets, if we square it, it will always be positive.
Exactly. You definitely correct. So in the Euclidean sense, if we say anyway, I won't give an illustration. Bianca has explained it very well. We don't want to have a negative value, so that's why we are squaring, because it can be negative. But anyway, once we do the squaring, we also then have to go in by the formula, get the square root. Once we evaluate what's inside the bracket, so we find the square root. So to the power half means that we are looking for the square root. Okay, so to work out to what? 2.1. Bianca has 4. How did you arrive at 4?
No, it's just an example to show that if you square a negative value, you will always get a positive.
Thank you. Thanks for that illustration. And then if you follow through the example, the distance here will be what? 2.1. Thanks so much, Bianca. Okay. So remember, we are just on sample 1. We then do the same thing. Now we now check to see what's the distance of sample 1 from M2. What is M2? M2 is a centroid of cluster 2. Okay, and then in this example, it's not shown on the screen here, but you'll have to follow the same formula. In this illustration, what is the distance? Sheldon. All right. So set 2, what's the distance here from M2? Okay. And the C where did you get 3.25? Okay, where did you get the 1.3?
Using the distance of 3.40 and 2.1.
Okay. That contribution came from, is that Sipiwe?
Yes.
Okay, so
Yes, it was just a wild guess. Yeah.
We have done two things here. The first thing we did was that we computed the distance of sample 1 from M1, and our answer is what? Sipiwe?
2.1.
2.1. Then we repeated the process to determine the distance of sample 1 from M2. And what is our answer?
3.40.
Okay. The question here is, where does sample 1 belong? Cluster 1 or cluster 2? Sesetu.
Sample 1 belongs to cluster 1.
Why? Because?
Is that not what we initially decided on?
The clearing distance is shorter.
Okay, so Sesetu, you are correct. It belongs to sample 1, but the reason is it's because it's much closer based on the distance that we've computed.
Okay.
Does it make sense?
Yes.
Okay, so we are saying that X1 is a member of cluster 1. All right, now Sesetu, we do the same thing for sample 2, sample 3, sample 4, and sample 5, right? Now I want you to look at sample 5. What is the distance of sample 5 from M1? What is the distance?
The 3.6.
Okay, and then the distance from M2?
2.01.
So my question is, where does sample 5 belong? Cluster 1 or cluster 2?
Cluster 1.
Cluster 2.
Cluster 2.
Cluster 2.
Okay, so Sesetu, it's cluster 2. The reason being?
Oh, the smaller distance.
We've looked at the distance, and then the numbers are telling us that sample 5 is much closer to M2. Are you clear now?
Yes.
All right. So this is step 2 of our K-means. All right. So there's been some reassignment going on here. All right. It doesn't end there. Step 3 means that we then do what? Remember that we've reassigned. Okay, so step 3, we now do what? We recompute the centroid. Okay, because we've reassigned the samples, we recompute the centroids. So we walked through the process of calculating the centroids, and what you will see is that M1 now, it works out to what? 0.5 comma what? 0.67. M2 is what? 5.0 comma 1.0. These are our new centroids. Okay. What is step 4? Step 4 means we repeat steps 2 and 3. Okay, what is step 2? Step 2 is where we check. What did we do in step 2? We looked at the distance of each of these samples from the centroid, and then we are able to see where does this sample belong to, cluster 1 or cluster 2, and we are able to shift. Okay, so you now do that. What has changed here? The centroid has changed to what you are seeing on the screen here. So you then also now recompute the distances, and then you reassign. That's step 2. Are you with me? Okay, so in this example, we initially started off with this cluster of cluster 1 and cluster 2, right? And then we've gone through the iterations of the k-means. So the way it works is, like I said, is that you're going to reach a point where you compute the distances, but there's no changes in the assignment of the sample. So the samples are still in the clusters that they were in prior to the iteration. That's when you then hold the what? The k-means iteration. Are we together? When there's no more reassignment happening. Bianca, is that clear?
Yep, that's clear.
Okay. My question here is which is better? The initial clusters, or maybe the ones we have now? There's been a bit of a change here. Which one is better, do you think?
I think it would be the second one, because it has brought, it is now grouping those that are closer to each other.
How do you know?
Because of those Euclidean distances that we were comparing when we were separating the centroids.
Okay, I will take that. Bianca?
Even if you go and plot it on a graph, you can see that point 1, 2, and 3 is closer to each other, and then 4 and 5 as well.
Yeah, you definitely correct. Now, before we jump the gun, Bianca figured it out by a visual inspection, and then Jesse figured it out by just having faith in our processing, just trusting that we calculated things correctly. And you are both correct. But just to add to your correctness, we can also calculate something called it's called square error. There's something called within cluster variation. So we can compute the variation within the cluster. Okay. Now, just illustratively, let's assume that this is a cluster A, and then we have cluster B. I asked you this earlier, but I will ask you again. What do we expect in terms of the variations within this cluster? What do we expect, just without overthinking? High variation or low variation? What do you expect?
Low variation.
Low variation. Why? Because for us to group these samples together, they have to be similar in some way. So within the cluster, we expect a low variation. Okay, what about between A and B? Let's say a sample in A and then a sample in B. What do we expect in terms of variation? We expect it to be high.
Variation.
Because it's one group versus the other, we expect it to be very different. Okay? It's a little bit like, let's say we are grouped by gender. If we take two guys, they'll look the same, maybe the same height. But if we take one person from the females, another person from the males, they'll look more different. Maybe one has much longer hair. You get my point. It's the same concept here. So the point here is that Bianca, we can calculate something called the square error, so we can do this objectively. Okay. So in other words, what we are saying is that if I could take you back here to the question, we can compute the error in the initial cluster assignment. We compute the error, maybe something called error. Okay, then we compute the error again in our fresh assignment here, and then we compute the error, and then we compare these two, and then see which one is high or low. All right, that is all that we're trying to do, and that is all that this formula here is trying to tell you. Okay, so in a way, what we look for is two things. One, it's what we call the within cluster variation. So we're looking for the error within each of these clusters. Okay, so once we've done, we get the error in cluster A, then cluster B, we can sum up these clusters to get the what? Something that we call the total error. Okay. How is this done? I've already shown you the formula. So the way you work it is that again we'll be making use of the centroid. Again, just to refresh your memory, you remember our two centroids here that we had calculated. You with me here? The first one is what? 1.66, 0.66. The other one is 3.25, 1.00. These are the centroids that we have. All right. So then how do we calculate the within cluster variation? All right. It's the same concept. Let's look at the X part. Let's look at cluster 1. I've highlighted cluster 1 here. What samples we have in cluster 1? Sesetu, can you give me just the samples that are in cluster 1?
We have sample 1, 2, and 3.
I need you to look again.
Oh, so not the revised one. 1, 2, and 4.
Okay. We are looking at the initial distribution. Okay.
Okay.
So again, what we would do is what we did earlier, where we look at the X component. You notice the 0 there. Notice the so this 0, it's the X part of X1. Then this 1.66, it's the X part of the centroid, right? Then we say plus. Where's the 2 coming from? The 2 is the Y part of our X1. Where is the 0.666 coming from? This is the Y part of our centroid here, as shown in the top right. Are you with me? And then we square whatever is in the brackets. Then we say plus. So if we say plus, what are we doing? We are going to the next sample, which is X2. Now notice that X2, the X and the Y part are both 0 and 0, which is why we have 0 there. I hope you can see where my mouse is. And then it's also 0 there. Nomvuyo, is it clear? Then we go to X3. Bianca, are you clear on how we are working things here?
Yep, understand.
All right. Ms. Okuhle, are you clear?
Yes, sir.
All right. So if you evaluate this, we'll end up at what? 19.366. Right? Now, if we are calling this error 1, meaning based on the initial assignment. All right. Now we can repeat the process. We are calling this error 2. No. I'm wrong there. Let me make the correction. Error 2 simply means that remember we have 2 clusters. So we are looking at the within cluster variation. So the one we've just looked at here, this is for cluster 1. Okay. E2, This is for what? For cluster 2. So E1 is what? 19.36. E2 is what? 8.12. So these are the within cluster variation in cluster 1 and then cluster 2 respectively. Mr. Kuhle, is that clear?
Yes, sir. Yes, sir.
And where is this? This is for the initial distribution. Okay. So we repeat the process. No. Before we repeat the process, we can add them up to get what we call the total error, denoted by capital E. So the total error will be what? 27.48. We simply added our two values here. This is a total error, meaning over everything. Okay. Then what we've done here is that we are simply calculating, we're repeating the same process, but we are now working with what? With a new cluster, so the ones that we had created after the first iteration. So if you repeat that process, our E1 comes down to what? 4.17. And then our E2 is what? 2.0. And then what's the total? We add them up. We get 6.17. All right. So coming back to the answer, which one is a better clustering? In other words, you need to look at 27.48 versus 6.17. Which one is better?
6.17.
Exactly. All right. So we can do this more objectively. And then, yeah, like Bianca said, yes, Ms. Okuhle, go ahead.
Yeah, so when we are doing these iterations, which margin of error is acceptable when you arrive at, for instance, I see we move from 27 to 6. So what is acceptable? Should you get to maybe below 2 or below 1, or anything below 10 is fine?
Thank you for that question. That's a very important question. So the question is, what is an acceptable error? We don't have a standard, so we in a way view these in relative terms. So relative terms meaning it's one versus the other. So in this case, we're simply saying the initial assignment versus the assignment after the first iteration, and then we conclude that this is better. We are not saying ideal, we're saying better than the other. So we always see these in relative terms. Okay? So remember that we can also have a third iteration. So a third iteration might actually give us maybe a lower value. But in this case, because it's a simple example, maybe it won't be any lower. But the point is, the lower the error, the better. Yes, Bianca.
I just have one question. So let's say, for example, we did a second iteration for this question, and we saw, okay, you know what, it converged. Will the square error of the second and then the third iteration be the same? Will this be an indication that it will converge?
So if there's no movements in the samples, then most likely the error will stay the same. And the way if I could take you back to the previous step here where we were here, step 2, what we were doing was that after calculating the centroids, we looked at the distance of the samples from each centroid to the sample, and then wherever the sample is closest, that's where we assign the sample. So hence these are changes here in the assignment. Now what happens at some point is that when you do this step, you realize that the samples are not moving. So the samples that were in cluster 1 are staying in cluster 1. Samples that were in cluster 2, they just remain in cluster 2, meaning no changes. That's how you know that you then terminate the iteration.
Oh, okay, makes sense. Thank you so much.
Any other question? Yeah, it could also be that, again, I'm just thinking based on the questions you've asked, you can have a situation where maybe there is a bit of a movement in the samples, but if you look at the error, it's not significantly different. Maybe it's just changing very minutely. Again, that could sometimes be an indication that you can halt the algorithm. Okay, any other question based on what we've done? Sipiwe? Sesetu?
Maybe just
I'm good,
a
thank you.
general one.
Mm-hmm.
Sorry. Yeah. I understand the math, but I'm still probably intrigued by the science behind, because obviously on supervised learning, the data was labeled, and maybe I'm just intrigued by how the machine starts clustering and what logic is behind. Yeah, maybe. Yeah, that's just something I'm intrigued by.
Yeah. That's a good comment. So there's two questions that you've asked. I hope that you remember the both questions that you've asked. One is about just the intrigue because the data is unlabeled. So let me perhaps say that what was that, Sipiwe?
Yes.
So just bear with me. I have to take you back here. So what he's saying is that our data is unlabeled here, and by that he means we don't know what each sample here means, right? We don't know. But what you've seen is that at the end of the day is that we end up with some kind of a clustering where maybe sample 1 ends up in cluster this or cluster that, right? We can start posing other questions based on what we see, and that's where the value of our clustering is. But let me not maybe go back. Maybe let me, instead of going back, let's go forward. So forward would be the pros and cons of using the k-means. Remember that there's several other algorithms that you can use. Now, why are we using k-means? I'll give you one. It's simple, and it does work. That's why we use it. It's computationally, what's the word? Let's say it works fine. Let's put it like that. It's not too complex. Some of the downsides are that there's very vague guidelines, for example, on what should you use for your value of k. In our example, I gave you k as 2, and so we were able to work through an example. But then how do you arrive at that value of k? We don't have guidelines, and that also hinges on the downsides of this approach. Another problem comes because you recall we said you start off with some random assignment of samples. So that can also affect how the k-means algorithm works. Because if that initial random assignment is good, you end up with maybe good performance going forward. But if it's bad, it might also complicate things. Yeah. And then if you've got outliers in the data, the algorithm doesn't work very well. Okay. Anybody wants to maybe just give us a simplified one line of what we mean when we say outlier? What's an outlier in the data? What are we meaning?
Maybe look at try saying extreme, an extreme.
Yeah. So an example is you know, where maybe I'm looking at let's say you are all working, and maybe let's just say that you all graduated with your undergrad maybe about the same time, and maybe you all earn I'm just making this up, let's say maybe you earn let's say 30,000 a month, right? And then maybe there's one guy here that earns maybe 3 times that amount per month, but there's just one. So we can call that person an outlier because it's not the normal. It's more like an isolated incidence. So we are saying that when you're doing classification and then there's outlier data points, this algorithm is what? It's very sensitive to such noise. In other words, it won't work very well. Why? Because as you can see, if you imagine what we mean by k-means, you're looking at the average. So if there's outliers, they will influence the average or the mean. Sounds good? Okay. Like I said, any other question?
Okay, it's me. So, I'm not sure whether the lesson is still going on or we're at the end. So first for me, is there any material that you can point us to gain more practice on this? And then two, when we're doing the practical of this, are we going to be using Python, or we're going to be using Excel, or we'll be using R, or which software are we going to be using? Thank you.
Yeah, that's a good question. What are we going to use for doing this? Again, I seem to be piling up on the questions. I'll power that one also. We'll deal with it somewhere towards the end. Mr. Guhle was saying, is this the end? No. We still have a few more slides to go to, but I promise I won't hold you up longer than is necessary. Maybe instead of me answering your question, I'll ask one, which is that how do we cluster data that's more than a few samples? In this example, we had 5 samples, and then how many features did we have? Just 2. But what if the data is large? How then do we do the clustering? And I think that's where Ms. Okuhle is going. But maybe let me bring that to you as in form of a question.
Yes, so obviously, yes, we will need assistance of a software to handle more samples. Yeah.
All right. So the point I'm making is that the example we looked at is deliberately simple because we need to have an understanding of the k-means algorithm. We need to know how it works. Okay, why do we need to know how it works? Well, this was developed by people. Is it perfect? No. If you know how it works, maybe you are going to come up with an enhanced version of the k-means. You might call it, I don't know, maybe k-means, enhanced or something. So this is why we dive into these algorithms. And Mr. Kudle is correct. If you have a larger data set, you can't work with it using pencil and paper. That's just not feasible. You need to have some tools that that can help you get the work done. So in light of this, I will, for example, I will show something here. Hey. Just bear with me, I'm almost there. Okay, so in this simple example, can you see it?
Yes, we can.
All right. So what I have is just some very simple data. Just an ID there, 1, 2, 3, 4 up until 25, and then a fictitious age there, and then a salary. We can assume that maybe this salary is in terms of $1,000 per year. We can maybe make that assumption. So I have this. So to try and work with this manually, it's a little bit too error prone. So what you can do is that you can, for example, use R programming, and then I will come to your question, Ms. Okuhle. So the way R programming works, in this case, I'm using R Studio. I won't walk you through each line by line, but I'll just say that what we are doing here is that we read that CSV file I showed you. Okay. I'm going to try and execute this code here. Okay, so before I go further, there's something called, remember we spoke about how challenging it is to determine the value of K. You remember we said that, right? So there's something called the elbow method. Okay, so the elbow method is something that is used to determine an optimal value of K. Okay, so how is this done? It's pretty much trial and error. So notice what we are doing here. If you check my x-axis here, I have 2, 4, 6, 8, and so forth, right? Then the y-axis here, this is where we then note the what we refer to as the within cluster sum of errors. You recall I showed you how to calculate the sum of errors. We did that, right?
Yes.
Yeah, so the way this method works, it's pretty much trial and error, meaning you try different values of K. Now notice what's happening to the total within cluster error. What is happening? It starts out very high when you have one cluster. So where there's this space here, this means that you have one cluster, meaning there's no clustering. So the moment you have two clusters, what happens to this sum of squares? It reduces, right? Can you see?
Yes.
Then come down to k is equal to 3, it reduces further. Now, the moment we hit 4, it reduces, but from 4, there's no more reduction that we are obtaining. So if we go 5, 6, 7, the total within cluster area, it stays the same. So we determine that our optimal value of k in this case is what? It's 4. Because this is where the elbow is. That's where the name comes from, the elbow, because it's curved like an elbow. So where it curves, we call that our optimal value. So 4 is optimal. Can we use 6? We can, but 6 doesn't give us any advantage. So it's a waste. So we stick to 4 as optimal. All right. Any questions on the elbow method? All right. As you can see, it's trial and error. So you in a way have to do this step to determine your optimal value of k, and then you work with that k. We do have other methods, as the name suggests. This is just one of the many methods called the elbow method, but there is other ways of determining the optimal value of k. So in this example, if we go further, the clustering will look like this. Okay, how many clusters do we have? We have 4. Okay. Sipiwe, are you there?
Yes, I'm here.
So our Y shows the salary, our X shows the age, and we have these 1, 2, 3, 4 clusters. What are some of the conclusions? How can you describe these clusters? How can you describe them?
So when I look at cluster 2, which is blue, it seems the age, the older you are, the higher the salary you get based on this. And then if I look at cluster 3, which is a bit strange, because the age comes after cluster 2, and the salary is very low in comparison, but the age is the 10-year difference, but it's not as big as cluster 1. Yeah, so, for me it looks like it's grouped by certain age groups to say if you belong into a certain age group, this is the amount of salary you get, but it's not linear in a way. To say if you are 40, you get a lower salary than 50. Yeah, that's what I'm picking up. Because you've got a younger age who's earning a very low salary, which is the cluster 4, for example. Yeah.
Yeah. So you are correct. But maybe you are saying the older you are, the higher the salary. So instead of seeing it that way, we can also read it just slightly different. So maybe we can also say that this is showing us the older people with a high salary. It's giving us a view of that. Okay, it's not saying the older you are, the more you pay, but we're saying that it's showing us visually the grouping of grown-ups with a high salary.
Yeah. That's no.
And then there's a lot that we can decipher from here. Remember, this is an example. Now, imagine that this is maybe data for the whole country. This could give us some insight in how maybe salaries are distributed across a population. Okay. Can I tell you what else you would be interested in, Simpiwe, since you are saying that you are fascinated by the logic here? Can I tell you what else would be of interest to you in the real sense here?
Yep.
You might also be interested in looking at the size of these clusters. You might say, okay, where is the concept? As an example, let's say cluster 2 is very small, right? And then maybe cluster 5, cluster 3 is very big. So that tells us that the older people earning a higher amount are very few. You get my point?
Oh yeah.
So
yeah.
so the sizes of the clusters can hint at something.
Okay. So you can still drill deep into the cluster itself to get some insights.
Exactly. We can do that. We can look at the cluster sizes themselves and then see what they are telling us. So this is here I used ARA programming, and then I was using ARA Studio to do this. I won't have the time to run you through line by line. Okay, so here the point is that you will have to find a tool that you can work with to use to do the clustering. And then here I won't dwell so much on this, but this is something that I strongly recommend that you do lots of reading on. So remember we said that K-means is just one of the many methods of partitional clustering. There are other methods. For example, there's something called the density-based approach. And there is an algorithm that for short, we just say dbScan. It's an alternative to K-means. There are instances where this it might work a lot better. And then you can also do some reading just to pick up on theoretically when is one more appropriate than the other. But what the textbook says is that dbScan is slightly a little bit more complicated computationally. And so it's more appropriate when, maybe data is of low dimension. In other words, data doesn't have that many features. So you can use a dbScan. Okay. I do have some notes on how it works. So it doesn't have the whole concept of K or anything like that. Instead, it looks at just how the density of the data points, and then it will form the clusters of varying shapes. So the shapes are not in a way fixed. Okay. Okay, I do have some summary notes for you to just explore how this dbScan works. Yeah, but the starting point for me would be that work through the K-means, master it, and then once you're happy, you can move on to dbScans. Like we said, the resulting shapes are likely to be potentially irregular, and this is how dbScan works because it's looking at the density of the points. Okay, and what you are seeing here are some real-world examples of dbScan in action. Okay, very weird shapes. Now I'm now back to the question that Simpiwe asked, which was the logic or the science behind. But rather than answer that question, I'm going to pose a different question here, which is let's maybe have a conversation on some of the application areas of clustering. where can we apply or how can we make use of this concept of clustering? Where do you see it being used? Jesse.
I think I've read somewhere where it talks about where a retailer maybe can be clustering consumers or customers and maybe then offering them maybe certain things according to the clusters.
Okay.
Based on maybe certain patterns.
We actually looked at one example where we looked at spending patterns, and then you told me about the way the grouping was done. Some they bought a large number of expensive things, others bought a few cheap things. Yeah, now just when the retailer does that, what do they then do with that information once they've done the grouping?
Maybe they're going to use it to offer maybe discounts or to offer those type of maybe customers maybe certain new products. See how maybe we are always swiping these cards at Woolies. So maybe later on they start maybe posting certain things to your email, or sometimes they've got your data based on your on those patterns. So it's for maybe for advertising.
You're correct. They can use it for what we call targeted marketing. So instead of airing an advert on TV, they will target you specifically. They might send you an SMS because they know that Richard likes buying cheap things. So the moment they have cheap things, they send you an advert directly, or they offer you a deal and say, if you buy this and that, get the other one free. We'll give it to you. But the point is that they are targeting you specifically. Thanks for that. Ketley's hand was up, and then we'll go to Ms. Okuhile from there.
Oh no, I wrote my answer in the chat. I was saying that banks and insurance can cluster customers according to their risk profiles and then offer rates according to their risk exposure or risk profile. It can also be done by insurances where they look at your risk profile as a customer and they could probably offer you lower insurance rates depending on where you fit in according to their risk profile. Yeah.
Okay. Now, how do they determine the risk?
Risk could be many variables: location, model of car, specific. Let's say for insurance, banking, it could be rate of lending, how much you lend, your payback, your how quick you pay back. It could also be
what do you mean how quick I pay back? I'm there asking for a loan at the bank.
Yes.
Mm-hmm.
I said banking and insurance. So in banking, they could be looking at number one, your credit score. They could also be looking at your exposure to other credit. How much other credit do you have? They could also look at how you pay or what kind of pay are you. Are you one that pays the minimum, or do you pay a little bit more, making you someone who pays up quicker than the contractors? And all of that will then determine whether or not you fit in a specific cluster. And then this cluster of people are then offered a rate of a certain amount. Let's say, for instance, we know that these ones in this group, maybe we can offer them loans between 15 and 20 or between 13 and 15% because their profiles are good. They are good they're not as exposed, and they have good credit they have good credit behavior. So we offer them a smaller, a rate. That's how I would think it would be used in banking. And then in insurance, that look at the different variables, where you're from, where you frequent, is your car covered, is your car sleeping outside, how many times do you drive the car, how long, how far, and all of that to then come up with a premium that they can charge you, a monthly premium for your insurance.
Yes, you are correct, Ms. Okuhle.
Yes, for me, this one, I think it will be largely used in population studies or maybe by the government to provide services to the population. So, yeah, you can cluster, or let me use the word group, people according to the education level, and according to the services that they need and require. For instance, sometimes you have statistics in here that in a certain town, HIV is high in that region. So then the government can streamline services specific for that town. Yeah.
Okay. All right. And anybody else with a different take? Okay, here's maybe my 2 cents on this that maybe you need to take away. So clustering can be done as part of pre-processing. So it means that there's some processing we want to do. Now, prior to doing that, we do some clustering. For what purpose? To get a glimpse of how our data is structured and distributed, we can do clustering. Okay. So we are, it's not the end in itself, but it's more of a means to something that we're working towards. As an example, you can use clustering as a way of identifying outliers. Okay, so as an example, let's say you have, maybe this is our plan here. Maybe you have one cluster there, maybe another one there, another one here. And then you have maybe a few data points somewhere very isolated here. You could maybe now view these as what? You could maybe view these as outliers. Okay. But we can also do the clustering as the analysis that we are interested in. For example, this can be done for customer segmentation. There's already been examples that you've given already. Our telecom companies, they do this all the time. So what they do is, remember that they have your information on how you use your phone. So based on that, they're able to do some clustering. How do they cluster? It depends. For example, they can maybe cluster based on there's people that use their phone at night. They make phone calls. Okay, so that could be one cluster. And then there's people that they don't use their phone after 7 p.m. They use it daytime. And then what does a telecom do? They do targeted marketing. They phone you and say, okay, pay this much, we'll give you these free minutes after midnight. You get the point I'm making. So they'll give you those very targeted deals because they understand you. So by creating the clustering, they're able to target those clusters. Okay. And then maybe just to let you in on what goes on backstage. So behind the scene, you do have, maybe data analysts that will do that work. So they'll do the clustering, meaning they'll draw up a list of, using the simple example I gave you, they can pull up a list of maybe subscribers that use a phone at night, okay? And then they pull up maybe another list of subscribers that tend to use SMSs a lot, and then they give that to marketing. The marketing guys, they know what to do. That's how it goes behind the scene. Are we together? Okay. So the list of applications, it's essentially endless. Simpiwe, does that help with that question you had on the logic?
Yeah, it does help. I think I'll do some more research to understand the sort of mathematical logic in terms of how it, because I guess the data is there, but no one is training it. It's just yeah, it's figuring things out by itself. So
did you follow that Kemin's example that we had? Did you follow through?
Not yet, but I did follow the logic in terms of what happens, yes, and how it derives and gets to the output. Yes, I did understand that. Yeah.
Yeah. So the summary I want to give is that the moment that you have, let's say this is a cluster, that's a cluster. Okay. You are then able to do some further interrogation to say, okay, what is it about this cluster? You can also maybe do some further interrogation about this cluster here. So in a way, clustering can facilitate some, further analysis that you are carrying out. Okay.
Yep.
So yes, Ms. Okuhle.
Yes, I know maybe it might be too much to ask, but if you do have a case study, it can even be brought where clustering was used along the way. Can you maybe just give us a link so that we can just go through it? It might make us understand exactly how it's applied.
All right. Definitely made note of that. Okay, you've mentioned the banking sector. We've spoken about customer segmentation. The point is there's lots of areas of application. I think Jesse spoke a lot about risk and how that's done. Yeah. Again, maybe just to give you a summary here without delaying you, to summarize what Jess was saying, if you signing up for an insurance product, maybe a car or anything, what the insurance company will do is that they'll collect some information from you, where you live, your age, blah, 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 blah. Then based on that, they will place you in a cluster. In other words, they group you. Are you high risk? Are you low risk? Then that determines how much you'll be paying for your insurance. Okay. As a very simple example, if you are a young driver, you pay more for insurance than older people. Am I correct? Because young drivers are seen to be, they're considered to be more riskier. Because, I don't know, young people tend to drive more dangerously on the road. That's a thinking that insurance companies have. Anybody who agrees with me on that? Yeah, so those of you that are much younger, you can maybe check how much you pay for insurance, then compare it with maybe how much your parents pay. You'd be shocked that you pay much, much more because you're seen as high risk. We've spoken about customer segmentation, so keep that in mind. Yeah. Okay. Any questions on what we've talked about? Susan? I see it's already 8:30, so I am winding down. Just bear with me. Any questions?
I don't have any questions.
All right. Larissa, Governor.
Nothing from my side.
Okay. There is an exercise in the lecture slides that I recommend you work through. It's simple. The idea is you use it to gauge your understanding of the K-means algorithm. So please try to work through it. And then a few notes here. These are my parting thoughts. I think I have 2 more slides and then I will let you go. So when you're doing clustering to get good results, we didn't have time to chat about this, but you might want to consider pre-processing your data. So pre-processing just means that you prepare it for whatever analysis you want to carry out. And then, yes, we said you can use clustering as a way of detecting outliers, but we can also say that to get good clustering results, you might also want to detect the outliers. So you eliminate the outliers from your data, and then you do the clustering without having those outliers in your data. That could be one way. And then some of the normal pre-processing you can do is, for example, normalization. So where you normalize the data. So this just helps in ensuring that you have, let me use the word, normalized distances. Okay. Are you okay with me explaining this table which is on the slide here? I promise I'll be quick. Can I go ahead? All right. So here it's just an example where we are using what's known as a min-max normalization. So the idea is that you want to ensure that, if you see, if I could maybe give you this data that I have here, can you see? Can you see that the range of values like varies? For example, there's a 22 here, and then there's also like 100 there, 65. It's a wide range. Have you seen that? So one normalization you can do is where you modify the value so that every value lies between 0 and 1. So you convert the values, and you can do this using what's known as min-max normalization. So let me give an example. You need to do this, you determine the maximum value and then minimum value in the data set. So in this example, our maximum value is what? It's 100. What is our minimum? Our minimum is what? 50. Okay. Then we replace this in our formula, as you can see. 50 minus 50 divided by what? By 50. Okay, where's the 50 coming from? It's coming from max minus min, which is 100 minus 50. So anyway, when you check on the far right here, notice that every value now is what? It's 0, 0.2. There's nothing above 1. There's nothing below 1. This is called min-max normalization. Are you with me? So what we've done is that we've transformed these values here from whatever they were to now in such that every value now is somewhere between 1 and 0. So this is something that you can do when you're clustering, because then the ranges now become uniform. Every range is between 0 and 1. There's nothing more than 0 and 1 in terms of the differences. That is normalization. And then as an additional point, we had these examples where we were able to come up with nice clusters. Okay, that's for illustration. In reality, the data may not be separated neatly. It's very messy. So you'll have to think about what your objective is and then maybe do more of this pre-processing so that you can have good results with your clustering. I thought of pointing that out. And then maybe in conclusion, where do you go to from here? And I think that this is something that Ms. Okuhle has been trying to raise. My suggestion would be work through the examples presented. I might have been rushing through some of the points, but work through so that you can understand the k-means algorithm. And then the moment that you do that, you need to explore tools that you can use. Let's maybe say data science tools / statistics tools that you can use, stats tools, to help you speed up the work. So in the way I was thinking about this, I have this theory that you should always put your front foot, your strong foot forward. What do I mean by that? I'm not so familiar with where you are coming from in terms of the background, so that I'm not so sure, but you can tell me. So I remember, for example, the last time I checked with the previous class that we had, you had access to something called Data Analysis 2-Pack, which is a Microsoft plugin in Excel. Is that still the case? Okay.
Yes, it's still there.
Yes.
All right. Now, the last time I checked, this plugin doesn't support clustering out of the box. In other words, you'll have to do lots of tweaking for you to do the clustering. Okay, I thought of just giving you a heads up. Okay, what I would like to add is that if you are, the kind of person that's very strong with Excel, there's other plugins that you can use. Remember that this 2-Pack is just a plugin. There's other third-party plugins that you can use. Okay, one example that I like to give is something called Excel Start. There's 2 versions. One is cloud-based, which is free, but again, the last time I checked, functionality is very limited. They do have a desktop version. Now, this is not free. It's a paid product. Okay, but the point is, I'm not trying to give them a free commercial. That's not my point. What I'm trying to point out is that there's several other spreadsheet-based plugins that are out there. And I'm not here to advertise any of them. I'm just saying that do what? What's my word here? Mr. Kuhle, what am I saying? You do what?
Explore.
You explore, okay? So what I like about these products is that most of them, they'll give you maybe a trial period. That's good. You try it out maybe 14 days. If you like it, maybe you can pay. If it's something that you'll be using in your everyday work, you can maybe pay for it, or you tell your employer to buy it for you. If it's just an assignment, 14 days is more than enough. You can use it for the assignment and you get done. That side. So you could go this way of the Excel plugins. Okay. Those of you that are inclined when it comes to programming, okay, in my example, I purposely used R. Do you have to use R? Not necessarily. If you already have Python experience, for example, I'll say that you should then work with Python if you have some Python expertise. And of course, you know that you might need to install some additional packages, but Python will get the work done for you. Okay. If you are not a programming person, maybe you are much stronger, maybe you coming from a math background, and then maybe you are interested in trying out this programming, then I would suggest that you focus on R programming. Okay, why? Because R programming was developed by statisticians to be used by statisticians. That's why I would recommend that you maybe focus on learning R. There's lots of online tutorials that you can follow. Okay, can you use Python? Yes, you can. Nothing wrong with that. I'll leave this up to you just to see what your inclination is. Okay, Mr. Kuhle, does that help?
Yes, no, it helps, and I would like to appeal to make an appeal to other classmates, even myself. If I find something that will help, I'll share. So if someone out there finds something that's especially free or open source and that can help in this case, please let's share the information. Thank you.
Thank you so much. That's a very good point that Mr. Kuhle makes. And then if when sharing, you also have to let your friends know, let them know whether it's free. That way, if you've spent 1-2 minutes figuring out, let your friend have a bit of an advantage, and yeah, you share new information. I support that. And then my emphasis here, before I lose you, is that this is my personal philosophy that you should put your strong foot forward. That's just my personal philosophy. And what do I mean in this context? I'm saying that if you are much stronger on the programming side, you could lean more, use the programming environments to do the work. Those of you that maybe you struggle with programming, but you are okay using a spreadsheet, I'm saying that instead of you struggling with programming, maybe you can have an excellent solution by using a spreadsheet-based plugin. Okay, so whatever floats the boat, the key word here is that you will have to explore. That's a key word. And don't be afraid. Python, other programming, they're designed to be easy. So if you've never tried it out, try it out. Okay? And then you share like Mr. Kuhle said. Anything else that I can help clarify? Going once, going twice? Okay. If there's nothing, I will end there, and then we'll catch up again next week around about the same time. Thanks so much for all your attention and for being attentive. Please have a pleasant remainder of the week. Yeah. You should have access to tutors, and then if there's anything that maybe you need me to assist with, the tutors they know where to find me. You can reach me via the tutors. I'm quite easy to reach. Yeah. Thanks again. Bye for now.
Thank you.
Thank you very much.
Bye bye.